Okay, a little more work on reaction quotients. This is something we've seen before. They give us a reaction, 2x plus 3y makes 2z, and they tell us the equilibrium constant is 0.145. Then they give us this totally different reaction. Do you see the connection between this and the original? It's all the same stuff, but the reaction's been flipped around. This one is x's and y's turning into z's. This is a z turning back into x's and y's. All the coefficients are the same, so these reactions are just reverses of each other. If you wrote the reaction quotient for this, it would be 2z over 2x. I'm sorry. It would be z to the 2 over x to the 2 and y to the 3. For this one, it would be x to the 2, y to the 3 over z to the 2. Reciprocal. You might have remembered that already. These are the exact same values except flipped upside down. So that means the equilibrium constant for this should be the same as this, only flipped upside down. The K for this reaction will be 1 over 0.145. And we can calculate that. It's going to be just under 7, I think. Yeah, 6.89. 6.89, 655, etc. Because this had 3 significant digits, when we flip it, we still get 3 sig digs, and so 6.90 should be correct. So anytime you take a reaction and just reverse it, it kind of reverses the equilibrium constant. You get 1 over the original value. Different thing here. They ask for a reaction quotient first of all, and that's easy enough to do. Our Q is CH3OH, that's methanol, over carbon monoxide and hydrogen. And that's wrong if I stop there. What else should it have in it? Got a coefficient of 2 here, so this should have a power of 2 on it. All right, so that's the reaction quotient. And now, this is the first time we're talking about Le Chatelier's principle. What are 4 things we could do to this system if we wanted it to make more methanol? For example, one answer is we could add more carbon monoxide. Why would that help? We know the system is trying to stay at an equilibrium level, so if we add more CO as a stress, the system is going to say, oh no you don't, I'm going to use up that CO you just added. And if I'm using up CO, I must use up hydrogen at the same time. And if I'm using up reactants, I must be making, oh look at that. Putting more CO into the system will provoke the system to make more methanol as it tries to get back to equilibrium. So add CO is one fix we could make. If this up arrow were on the hydrogen, the same thing would happen. The system would use up CO and use up hydrogen, trying to get the hydrogen back into balance. In the process, it would, again, make more methanol. So add H2 would be another valid solution. What else is there? What other ways can we get more methanol out? We know more CO does it. We know more hydrogen does it. Well, one trick you can use if you're running a methanol factory is remove methanol. If you take this out, the system goes, rats, where's all that methanol I just made? I better make more to replace it. And so it'll use up CO, use up hydrogen, make more methanol to replace what's been taken out. You can imagine a cook who makes cookies, you steal the cookies, the cook goes, sacre bleu, and makes more cookies. And as long as you keep stealing the cookies, the cook keeps trying to get an equilibrium going, and they keep producing more cookies to try to fill the gap. So in a system like this, you can steal the product and it'll replace it with more product. That's another valid trick. So add CO, add H2, remove CH3OH, and that's all three of the substances in this reaction. So if we need four things, what else do we actually do? One tricky thing you could do is manipulate the temperature. We've told you that the equilibrium constant changes when you warm up or cool down the system. So you could experiment with running this system hotter or colder. That'll give you a different K. And if you can get the K higher, that'll result in more methanol being made. That's a good trick. And the last possibility we have is you can change the container size. In this system, we have 3 moles of gas on the left and only 1 on the right. So the right side is smaller. If you crush this system down into a smaller container, use a piston or something and just force it to be smaller, when you put pressure on something and try to force it down to a smaller size, it tries to reshape itself. And chemical systems do that by going, I'm taking up 3 units of space when I'm on the left. I only take up 1 unit of space when I'm on the right. I can cram 3 molecules together here and make 1 molecule, and that'll reconfigure me to a smaller size. So if you go smaller container, the system will run to get to this side because it takes up less space there. It's like it's trying to get the pressure off itself by shrinking down. So, all good tricks. Hope that made sense, and I'll see you in the next thing.